Okay, so we'll do, so basically we're going to talk a whole bunch about logarithms tonight, okay? So what I want to do kind of first of all, before we really get into talking about logarithms, is to show you this GeoGebra thing I came up with. Okay, so I'm not even going to really write anymore. I'm going to zip into this here. Ooh. I'm going to go to this, and it's going to take me a couple minutes to get into it here. Figures doesn't remember me. That's what I thought. Let's try this one. Ah, there we go. Okay, so here's what I have here. I have this y equals x line, which you might remember from when we were talking about functions and inverses. Okay, in that remember if we had a function here, okay, and you reflected it over on this side, then that would be its inverse. Okay, so what I did is I have a point P here that's reflected down to this point, and I'm going to slide this A. And then I'm going to kind of back off of this a little bit. We might try it again so that you can see it better. There it is. Every time I click off, though, it kind of makes it. There we go. Okay, so here I have this graph here, all right, on the top part. And this is the graph y equals 2 to the x, all right? So that's just a y equals 2 to the x there. But this is the inverse of it, okay? So this would be the reflection. So every one of these points, in fact, that's all I did is I made these points, all right? And then I just reflected them over off to this line here on this side, okay? So this y equals 2 to the x has an inverse, and the inverse is a logarithm. Okay, so this graph down here is a log. So if we were to go y equals log with a special base of 2, I would get the same curve here. I don't know if I can let me input that or not. Let me go up to here. No. It's probably not going to let me, I don't think it's going to let me input it, because I didn't really design it to do that. So anyway, that's what that is, okay? So the inverse of an exponential is a logarithm. That's the deal on that. And they have another thing on here too. It's not too bad, but I kind of wanted to do something like that. So let's go back to this. I'll leave that up there for later if you want to look at it. So if I have this, y equals 2 to the x, all right, then the inverse of that is a logarithm, y equals log base 2 of x, okay? So this, y equals 2 to the x looks like this, and then we have this y equals x line, so then the inverse looks like that, okay? So an exponential has a graph that in this case grows quickly, but a logarithm grows quickly and then levels out. See, it kind of flat and goes and flat. So it's kind of just the inverse because they're inverses of each other. All right. So the big idea here is this definition of a logarithm that you use a lot, okay? And this is what it says, that y equals b to the x, then the log base b of y equals x, okay? This is the definition of a logarithm right here. I'm going to see if I can pull up a calculator to kind of show you. You can do this very easy in Desmos, but then I have to be jumping back and forth. Yeah, I can do it on this. All right, so let's take a look at some of this for example. Let's say we have 3 to the second. Well, 3 to the second is 9, okay? So that means that the log base 3 of 9 is equal to 2. So here, this is your base, okay? It's always going to be the base of the logarithm. And basically, the x's and the y's here are switched, okay? So like 2 is normally your x, but over here, 2 is our y. 9 would be the y, but over here, it's our x. So they kind of switch. That's what's happening there. So one to really look at is like 10 to the 4th. Written as a log, that's going to be the log base 10 of this number is equal to 4. Yep. And we can check that out. Let me see how this calculator handles it. There it is. Okay. Now, when you're doing logarithms in Desmos, okay, there's 2 types. One is just a log. When you see just a log, that's called a common logarithm. And the base is always 10. Okay, because that's our base, counting base, obviously. So the base is always 10. If you see a log with a little a down here, then that means you can enter the base. So you can make the base anything that you want. All right? But base 10 is called the common logarithm. So if you ever encounter a log, L-O-G, with nothing else there, the base is automatically 10. Okay, automatically. Now, if you encounter this is called a natural log. Okay, and that base is E. That's that special number E that we had before. All right? So there's a common log, there's a log where you enter the base, and then there's a natural log, Ln, that has a base of E. Okay, so if you go into Desmos, which we will a little bit, I guess, here to take a look at some stuff, you'll see there's 3 choices for logs. You know, how do I know which one to use? Well, log is just base 10. Log you can enter any base you want. Ln is a base of E. But the definition of a logarithm is the key. That is the important thing. Okay. let's do this first. So here's some questions they're going to ask you to do. Change the exponential to a log. All right, let's try this out. So if we have 5 to the 4th is equal to 625, we want to write this as a logarithm. So you kind of want to pick out that base first, right? So we're going to have the log. What's the base of that? 5, good. And what are we going to take the log of? 625, okay, because, right, normally this would be the x, this would be the y, but here they're going to switch because it's an inverse, and x's and y's switch. And this would be 5, okay? So if I go into my calculator here and I go 625, or Desmos, whatever you want, log, oh, I can't do it because I don't have the right base. See, here it's really hard to do because I don't have a key that lets me put any base I want in there. So I have to do it a little differently. Oh, knock it off. There's the 4 I was looking for. Oh, this isn't 5. This has got to be 4. I don't know why I wrote a 5 there. Okay. So let's try another one. Let's go with 2 to the 6th is equal to 64. Then the log, what's the base? 2 to what? What are we going to take the log of? 64, and what's that supposed to equal? 6. Yeah. And if you try it out, you'll see it works. Okay. Are you able to see are you able to find those log things okay in Desmos? All right. Have you tried it yet? The log A, changing that base. Logarithms do have some applications in pH and in earthquakes, decibels, some applications there. Okay, so now let's go the opposite direction. So now we're going to write each log as an exponential. So here if I have the log of 1 with, there we go, that would be 5. So we're going to write this as an exponential. So we should really figure out what the base is. What's the base of that? Good. Because there's nothing written down here, right? If there's nothing written down, then the base is automatically 10. So we got 10 there. That's our base. So 10 to what power? To the 5th is equal to 1 with 5 zeros. Okay? And again, see how this is just switching here. This is your y here, but it's your x on this side. Because it's again, they're inverses, so the domain and the range switch. Okay, what's the base on this one? 3 to what power? 4 equals 81. That's how you do it. Okay? That's how you write them back and forth like that. Let's see here. They want you to find the exact value. So decimals probably won't work in a situation like this. And they give us a log of 1/2 of 16 is equal to what? Okay, so I'll just put an X here. Here's what we're going to do. All right, we're going to take and use a definition of a logarithm on this. So you use the definition of a logarithm a lot on these. So you kind of got to know it. So we're going to take the base, that's this, to this power here, and that's going to equal 16. So you say, well, that doesn't help us at all. Well, here's what we got to do. We got to remember that 16 can be written as a power of 2. So it'd be 2 to the 4th. So that's a little better because now we have a couple of 2's here, here, and here. Okay? So now let's take this and rewrite it so it's a power of 2. And then I can go from there. So this would be 2 to what power are we going to put right there? Negative x. Good. I heard -1, negative x. You got the idea. Now, from the assignment, those two things are the same. So we just need to concentrate on the top parts. So then what does x got to be equal to here? -4. All right, but we use the definition of a logarithm in the beginning to help us with that. Let's do another one like that. So let's go with the log of the square root of 3, log base square root of 3 of 9 equals, don't know. So we're going to use the definition of a logarithm. Here's our base. Square root of 3 to what power? X has got to equal 9. Okay. So again, see, this is the key. I have this 3 here. All right. So if I can get this in terms of 3, I'm going to be in good shape. So how would we write 9 in terms of 3? 3 to the what? 3 squared, good. Okay. Now I got to do this other side. This one I'm not sure you remember, but this is going to be 3 to what power would that be for a root? Let's see if you can get it.
It's 1/3 power.
Close.
1/2 power.
1/2 power. So that looks like that then. Okay. Well, because this is a square root. Okay. So a root is a fractional exponent. So whatever, like this is a square root, which is a 2, so that'd be a 2. If it was a cube root, this would be a 3. If it was a fourth root, this would be a 4. Okay. Did we do any of that when we did exponents?
We didn't do the square root.
I don't think we did roots, and I was a little concerned about that when I saw some of this and thinking that I don't know if we ever did any of that. I didn't think we did, so I don't know. I don't really know where that is. If some of you took Math 95 or not, I can't remember. It might be in there. I think it kind of is,
Yeah, we went over it in my last class.
Did you? Okay.
Square root. In my 95 class, we went over small letter. Yeah. Because if you depend on your calculator, you don't have like a cube root, but you have to put
Put in the, yeah, yeah. Okay. I couldn't remember where it was at. So now we're just going to focus on this since the two bases are the same. So what does x got to be? 4. Yeah. All right. Okay, but we're using the definition of a logarithm right off the top there to figure it out. Okay. Is there any questions on those things that we did right there?
But the last part, you just multiply it by 2, right? Get rid of the...
Oh, yeah. Or you can divide by half. Well, I mean, 2 divided by half. You can put that in decimals or whatever. It'd be pretty easy. Yeah, whatever you want to do. So let's take a couple minutes and graph a logarithmic function here. So let me get, there we go. And we'll graph one. So I'm going to just kind of go back to this. Clear this out, clear this out, clear this out. Y equals functions. So here's logs over here in the miscellaneous. And here they are. So there's log where you choose the base. There's a natural log. All right, so they're all right there. I'm just going to go base 10 here of x. All right. So there that is. Let me put on a projector mode so you can see better. So here's our log base 10 graph. All right. Notice that it never goes down here. It won't even let me trace it anymore. Okay, so it bends right along that axis. Okay. So you say, well, can you take the log of 0? Let's check that out. Undefined. You say, well, that's kind of weird. Why is that? Well, let's take a look at it. So if we use the definition and wrote it as an exponential, what would it look like? 10 to the y. 10 to the y is equal to... Can we take 10 to any power and get a 0? No. There's nothing. 10 to the 0 is 1. And anything either side of 0 is going to be a decimal, so you're still going to get a power. You're not going to get 0. All right. So that's why it doesn't work. Okay? You can't. It doesn't work there. All right. So there is no, it gets real close to 0, but never ever touches it. Same thing with a negative. And we can do the same thing here. And we're not going to get it to work. Okay? So the definition comes in there. All right, so we took care of that. And if we put a number out in front here, back to home. All right, just like before, it's going to be a vertical stretch. You can see that it's stretching it upward. Okay, number in front, vertical stretch. Okay. If I put something in here, it's going to move it along that x-axis. D is going to move it up and down. Okay. Doesn't look like it, but it looks almost like stretching it, but it's moving it up and down. Okay. Just like all the other stuff that we were doing before. A is this vertical stretch. C is a translation left and right. D is one up and down. Okay. Doesn't change anything.
And there's no reflection against the y-axis. There's no negative.
Yeah, so you're going to get a reflection of y-axis. Because you're taking these, like -5, and you would make it positive, so that's why it works. Right. And then there's also one here. Well, of course, I think we saw that. There's your reflection. The pivot's on that point there. Right. Okay. Anyway, that's what a log function looks like, graphed. Okay, never crosses this way, comes up. You know, unless of course you translate it somehow, then you can manipulate it, right, to move it back and forth. But in general cases, that's what it looks like. All right, and just really increases gradually. All right. Let's see. And natural law is going to look the same way. Nothing much different, just the base is E. They have a lot of stuff about the translation graphs, a little bit on that. Domain then of a log. What's a domain of a log? Just a normal one. Let me get rid of all these things here so we don't have anything in front of it.
X is greater than 0.
So x is greater than 0 because we can't take 0 or any negatives, right? So x is greater than 0. And the range? All real numbers. Eventually it's going to get there. It's just going to take a long time, right, in a logarithm. Okay, so domain, x is greater than 0, range, it's going to eventually get there, it's going to be all real numbers. That's a logarithm. Okay. Well, go take your little 5-10 minute break here, and then we'll do some more stuff with logarithms. Oh, change colors. Okay, I think everybody's back. So, let me get this back on here for us. All right. So let's do some more things with logs that is in this particular section. I'm not going to do a whole lot with the graphing part because, well, you can do that. All right. There's also some calculator stuff, but again, that's not that bad. You just type it in to Desmos or whatever. And I can give you some of those. But these ones here are a little bit trickier, so I would like to take a look at some of these problems. All right. Log of base 5 of x is equal to 3. Okay. So let's do some of these types. So in these x's are going to be here. Okay. They're going to be here, and they're going to be here. All right, so every time that they're in a different spot, it changes the problem a little bit, but it's not going to change what we're going to do. Okay, so to figure this out, we're going to use a definition of a logarithm. Because see, remember, we just use it all the time. So what's the base? So we're going to go 5, right? 5 to what power is going to be equal to, see how that is? Right? So this problem, it's looked kind of complicated. Once we use a definition of a logarithm, oh heck, we can get that. Okay, we can get that. All right, so it looked kind of complicated, but shoot, we use a definition of a logarithm, done. Okay. So let's try one with well, this one would be pretty simple if we put x there. Okay, here you're just going to go ahead and just take the log of 729 base 3, and you get the answer. You could use a definition on it, but the definition isn't going to take you anywhere. It's just going to take you to that. All right, so that really doesn't help us. So here, we would just find out what the log of 729 is. I think that works. Oh, base 3. I can't do it. You guys are going to have to do it. I guess I can do it, but it's not real easy. 6. Okay. All right, so now let's try one like this. Let's put the x here, and we're going to put 1/16 there. And let's go 4 here. All right, so using the definition of a logarithm, actually maybe this should be 2. Oh, that's okay. All right. So, what is our base going to be? So, x to the 4th is going to be equal to 1/16. All right, so, again, this looks pretty complicated. This may be not so bad. How would we figure this out? How do we get rid of that x to the 4th? How would you get rid of it if it was x to the squared? Square root. What if it was x to the 3rd? So we're going to do a 4th root then. We'll do a 4th root. So yours is going to be way easier than mine's going to be on this. Let's see. So 1 divided by 16 to the 1/4 power, and I get 0.5, I think it is. Okay, or 1/2. All right. So all I'm doing is using that definition of a logarithm on these. Okay? That's it. So no matter what the arrangement, use the definition of a logarithm, and you'll be fine. Oh, let's do this. And let me do one like this, because there's some of these on here. Oops, that was bad. Didn't mean to do that. I lost it. There it is. Okay, so now here the exponent. This is a difference, not written as a log. It's written as an exponent with the variable in the exponent. Okay, so there's actually a couple ways we can do this too. We can, since it's an e, I'd probably want to do the natural log, right? So the natural log base is e. What are we going to take the natural log of? What number is going to go in there? 1/3. And what's it going to be equal to? -2x. So here we're saying, well, okay, so now I just kind of went backwards and wrote it as a logarithm. E is the base. So that's going to be a natural log. Okay? So now it's just to go ahead and work this out. So I need the natural log of 1/3. So I'll just take 1/3. I don't take the natural log of it. I think I have that on here. Let's see, maybe not. Maybe if I push this, I'll find natural log. There it is. So it says mine says -1.0986 is equal to -2x. Divide by -2. Divide by -2. So it's just 0.54, right? Okay. So again, we're still using the definition of a logarithm, it's just that we're using it in the reverse. Okay? Anytime you see a solving equation, you're probably going to use the definition of a logarithm on it. That's pretty much everything that's in that section, besides a bunch of graphs. Did you want to look at that 119 problem that was in there?
Yeah.
You can look at that real quick.
I don't know if it's like the values on my calculator or I need to change some of the functions. But I keep getting the wrong. Unless there's a special way that I need to look at it.
So we want to find the height of an aircraft if the atmospheric pressure is 320 millimeters of mercury, correct? So the 320 is going to go where? Is it going to go for the P of H or is it going to go for the H?
P of H.
Right. That's a good question to ask. So let's do some work here. What should we do to get solve for H? What should we do first? Yes. Okay, here we go. So we have a couple of different options here, but one option, just use the definition of the natural log or logarithm, right?
Okay.
So we have E, our natural log, right? That's our base, E. What are we going to take the natural log of?
0.42105.
0.42105, right? And then that's going to be equal to what?
Negative 0.145H.
There we go. Okay. So now I'm going to go back to this. I'm even going to just say, hey, can you take the natural log of that for me? It's going to tell me that it's negative 0.86 and a whole bunch of stuff.
That's what I can get it as the answer, but it says that the answer is...
Well, I still have to divide, though.
Oh, that's why. Okay. Like 5.97.
So now if I divide this by 0.145, 5.96, there we go. Yep. So that's what you want, again, that's that definition of a logarithm. It just comes up over and over and over again. There's another healing of the wounds on there. How about that? There's a couple things on here. It talks about the Richter scale, okay, and just for a little bit of side note, if you have an earthquake of a magnitude 4, okay, versus an earthquake of a magnitude 6, right? The difference there is only 2, but what happens with Richter scale and magnitude is it changes by powers of 10. All right? So it's 10 times more powerful as you change in the Richter scale. So this would be 10 to the second or 100 times more stronger. They have a tough time measuring the powerfulness or the strength of an earthquake actually, whether it's sometimes they call it intensity, sometimes they call it power. I don't know what they're calling it here, but the magnitude of it, okay? But Richter scale is a perfect example of a log because here, look, see, if you take the log of 100, you're going to get 2, right? So, same with pH. Exactly. And decibels too are also that way. Okay, so that's where the applications of logs come in anyway, so you know that there's some stuff there. Okay. Okay, hang in there. Here we go. Let's do 4.5. Gosh, dang it. How many times am I going to do that tonight here? Okay. 4.5 talks about properties of logarithms. So I'm just on a side here, on the side, we're going to put properties. You can write this if you want, you don't have to. Properties of exponents, EXP. And over here, I'm going to put properties of logs. Okay. So we have three basic properties of exponents. And one of them is that if I take a to the n power times a to the m power, then we're going to take and we're going to add the exponents. Okay? So like x to the second times x to the fourth is x to the sixth. Okay? We're going to add the exponents. Since logs are an inverse of exponentials, that same thing can be with a log. So if we have log of a plus the log of b, then that's equal to the log of a times b. All right? So here, try to make this. If I have two logs that are two things inside that are being multiplied, then that would be the same as adding. So here we're multiplying and we're adding. Okay, so it's the same type of idea. So if we have a, oops, let me be consistent here. If we have a to the n over a to the m, then what do we do with those exponents? Subtract. So the corresponding log thing is going to be like this. Log of a minus the log of b is equal to the log of a over b. All right, so it's the same thing. Here, if we have a to the m to the n, then we multiply those exponents. So in logs, if we have a log of b to the a, then that a pops out in front, and we get this. A log b. So those are our properties of exponents. Now they add a couple more in the book. Okay, I'll just put them down here. They have a, if we have a to the log base a of m, then basically what happens is these a's cancel out and you just get whatever m is. Okay, you hardly ever use that property, but they mention it. And then they also mention this one, the log of a to the r base a is equal to r, which if you use the definition of a logarithm on, it would work out anyway. So I really don't know if this one's really that important. So I don't know. They mention it. We'll do some examples with these. I really don't know if this one's all that important. On page 329, if you got your books with you, 329, in the middle of the page, I'm not going to write this down, I'm just going to mention it to you. They have something called the change of base formula. So if you have a calculator with only base 10 on it, then you can use the change of base to figure out what the answer is. And you can see it says the log of m base a is equal to the log of m over the log of a. Now they put a b there, but you're going to make it a 10 because if you don't have a calculator that can handle b's, then you got to go with 10. I don't even know why they put b there. Desmos will take any base you want. Most calculators these days will do that. Okay, shoot, you can probably find one on the internet and do that for you. All right, so change of base formula, it's kind of outdated itself nowadays. You just don't use it anymore. All right, here's what this is what they're going to want you to do. They're going to say, write each expression as a sum slash and or difference. Of logs. Okay, so they're going to give you this here, something like this, the log, any base you want, of x squared over y, something like that. Okay? So what we're going to do is go up to our properties of logarithms and rewrite this as a expression of sum and differences of logs. Okay, so I go up here, all right, and I see that the log of a over b is equal to the log of a minus the log of b. So that's what I'm going to do. So I'm going to take the log of x squared minus the log of y, okay, but I have a property for this too. That 2 is going to pop out in front, so I get this. Okay, that's it. So you've taken it and you've broken it down into a subtraction of logs. And that's what they want you to do there. So let's try another one. Let's go with the log of 4x over z like this. Okay, so we got the log. What's this going to look like? We got 4x on the top, so what would that be? Log 4. Let's go and look at our property. Okay, a plus b. A times b is equal to a plus b. This is 4 times x, so that's going to be log 4 plus log x. It's a division, so what does that mean? What operation is that? Subtraction log z. Okay. It's going to look like that. Okay? All you're doing is just using those properties. Okay? Then in the same idea, they're going to have you write each expression as a single log. So here, we're going to go backwards. All right, so if we have 2 log u minus log v, all right, now we're going to go backwards, okay? So it's going to be the log u squared minus means what operation? Divide, and what are we dividing by? V. Now we wrote it as a single log. Okay, so we're just using those same properties. We're just going backwards with them. Okay, so we're going one way and then backwards, going back and forth. That's all we're doing. They even put some expressions in here, something like this. And the bases don't matter. You can put any base you want. As long as they're the same, it doesn't matter. Okay, let's see what this one's going to be. So we know we're going to have a log. What do we got? We have a minus, so what does that mean we're going to do? Divide. What are we dividing? X squared minus 1. No, this 2 is with the x squared, so it stays. Yeah. But what about this?
Yeah, that would go over the parentheses of x plus 1.
Right, so that's going to be x plus 1 cubed. So that's what that's going to look like. Okay, so don't let all this stuff mess with you. Okay, you're still doing the same thing. It doesn't matter whether it's an expression or whether it's a number or variable or whatever. You're still using the same thing. I'm looking to see if there's anything else in here that man, that's pretty much it. It's all just using properties of logarithms and the definition. But I can give you some problems to work with and play around with them. Since we got a little bit of time, I think. Yeah, a little bit of time maybe. Any questions on the properties of logarithms though? Let's try a couple of them. I think we got a little bit of time. I think we'll be okay there. Let's do one of these. Yeah, 27 is one then. That's a good one. That's a calculator thing, that's not so bad. I don't know. All those are pretty straightforward there. Let's see some more smooth. First one, 231. Let's do 14. 31. There. Try those ones out, see how those go. There's 4 of them. Okay. Then if you got questions on them, you can ask. I don't know if I have time to go over them, but